concrete. So one of the things that you could do along the lines of this independence assumptions is try to be more nuanced about your independence. So what do I mean by that? So just do not make this assumption that everything is independent of one another given the class, right. So think of something like this. I want to look at this joint distribution. I want to look at this joint distribution x1 to xp. So I am going to say things like, okay, I am going to write something more, okay, I am not stopping. So what I am saying here is, given x2, right, x1 is independent of everything else. If I know what the value x2 is, x1 is independent of everything else. Oh no, before that let me motivate it this way, this makes it a little easier for you to grasp. Yeah, people agree? Right. So I can write probability of x1 to xp as a probability of all of these conditionals. Yes? Okay, great. So now I am saying, hey, I am trying to find out what is the probability of x1 given x2, x3, x4 all the way up till xp. Likewise I am trying to find the probability of x2 given x3. I mean there is some arbitrary ordering I have chosen x1 to xp, right, it could be any other ordering. Now the probability of x2 given x3 to xp and so on and so forth. Now I am going to tell you that, hey, this is, I mean you can always add a conditioning g if you want, right, this makes my life easier if you do not put everything conditioned on g, right, if you want you can do that as well, right. So what I am going to say is, this is really not going to happen, you know. How likely is it that each of my variable like x1 is going to depend on the value taken by every other variable in my system, especially if I am going to have 30 and 40 variables, how likely is that x1 is going to depend directly on all the other 30, 40 variables in the system, right, that is not going to happen, right. So what will happen is, let us say that this is equivalent to saying it is something like probability of x1 given x2 comma x3, probability of x3 given x6 comma x7 to probability of blah blah blah, right, all the way up till, let us write another example. Oh well, that's okay, it's fine, right. So maybe my system is like this. So what does it mean? So x1 is dependent only on x2 and x3, given x2 and x3, x1 is independent of all the other variables in the system. Likewise given x6 and x7, x3 is independent of all the other variables in the system, right. Given x4 and given x5, x4 is independent of everything else, and x5 is independent of everything else just by itself, right, it is independent of everything else, and x6 depends only on x7 and x7 is independent of everything else. I mean there is just one way of writing it, right. Whenever I say x6 is dependent on x7, I can always flip it around and say x7 is dependent on x6. I am not talking about causal directions here, I am not saying that x7 causes x6, right. I am just saying that the probability distribution can be factored in the form of x6 given x7 into x7, right. Otherwise I can also do it as probability of x7 given x6 into probability of x6, right. I could try and do the factorization the other way, okay. I just want you to keep in mind there is nothing sacrosanct about the way I have done the factorization, right. It is just a convenient way of representing these things, okay. Right. Does it make sense? Like I said, if you are worried about the classification scenario, you can add a conditioning on G everywhere, right, that is typically what we do. But this kind of way of factoring things is more powerful than just using it for classification, right. You can use it for learning about any probability distribution, okay. It does not have to necessarily be about classification, you can use it for representing any probability distribution, okay. Right. So one way of, I mean this looks a little hard to track, right. So one way of specifying these kinds of conditional independence relations is to use a graph, right. So what will I do in this case? I will have a graph that has 7 nodes, so one node corresponding to each feature, right. What are the features here? More generally the features here are random variables, right. So x1 is a random variable that will take the value in whatever range x1 can take and so on and so forth. These are all random variables. So I am going to have is there something that is missing here? Yeah. So I have connected the graph now, okay. So I have x1 okay. So x1 depends on x2 and x3, so I will put arrows, okay. x3 depends on x6 and x7, and x2 depends on x4, x4 depends on x5, and x6 depends on x7. Right. So this graph structure, right, gives me the dependency or independence, conditional independence relation I wrote in that expression there, right. Make sense, right. So if you remember, when I was talking to you about the interpretation of conditional independence there, I said if you do not know what the class is, then Dhoni and cricket might become dependent, but if you know what the class is, Dhoni and cricket are independent, right. I mean occurrence of the words, right. I was telling you about that, right. Likewise, right, if I know what x2 is, right, x4 and x1 are independent, right. Is that clear? If I know what x2 is, then x4 and x1 are independent, but if I do not know what x2 is, then x4 and x1 become dependent. So what do I mean by that? If I know something about x4, then I can tell you something about x1, right. So if that is a little confusing, we will try to make this concrete. Let us say this can take values 0 and 1, and this can take values 0 and 1, not that it is confined to binary things, right, Boolean things, but makes it easier for me to write. So let us say that the probability of, right, something like this, right. So x2 basically copies x4 with a high probability, right, and likewise, so right. So that is x2 x3, so I will have to write a table like this for x1, right, and okay, yeah. So basically it says that when x2 is 0, okay, the probability of the x1 being 0 is low and probability of x1 being 1 is high, right, and likewise when x2 is 1, the probability of x1 being 0 is high, the probability of x1 being 0 is low. That is essentially what I am saying there, okay. So now if I know what x2 is, right, let us say that I tell you that x2 is equal to 0. Now the fact that x4 equal to 1, when if I say x2 is 0, then I know that the probability of x1 being 1 will be high, right, regardless of the value of x3, because that is the way I have written this thing down. But if I know value of x3 also, then I will know that, okay, whether it is 0.9 or 0.8, right. Now if I tell you that x4 is 1, it does not matter, because the only way x4 will give me any information about x1 is through x2, but I know x2 is already 0, right. But suppose I do not know that x2 is 0, but I tell you that x4 is 1, right, immediately what you know that the probability of x2 being 1 is higher, right, therefore the probability of x1 being 0 is higher, right. If I had not told you the value of x2, but if I had told you the value of x2, I say that okay, x4 is 1, right, but there is a small chance that x2 can be 0, right. So x2 actually becomes 0, in which case the conclusions you can draw about x1 completely changes, right. This is a very dramatic example, but it does not always be so dramatic, but the point I am making is because of the way I have drawn these arrows, right, if x2 is not known, knowing x4 will tell me something about x1. If x2 is known, then knowing x4 will not tell me anything more about x1. So everything that I can know about x1 by knowing x4, I have already extracted by knowing x2, okay. Is it clear? Right, so this is this whole idea of conditional independence and why this kind of a graphical representation helps us, right. So knowing x4, x3, right, not x2, I know only x3 but not x2, still does not disconnect me from x4, right, because the paths are very different. So x2, x4 can still influence x1 if I do not know x2 but know x3, okay. Is it clear?
So what if we have a kind of branch?
We will come to that, right. So this is just the initial setup, right. So what these kinds of graphical models do, or rather this kind of these are called called a Bayesian network, right, sometimes called a belief network, and sometimes called a Bayesian belief network, okay. So I mean you will find all the terminology in literature, you will find a Bayesian network, belief networks and Bayesian belief networks, and so in a Bayesian network is a DAG, okay, it has to be a acyclic graph, right, because if it has cycles in it you are basically messed up, right, because of the semantics of the thing, right. So we will actually talk about a graph representation which does not have any arrows even, right, which actually is an undirected graph. So undirected graph you can start talking about cycles, we will come to that in the next class, but when you are talking about a directed graph representation, right, it has to have no cycles, because if it has cycles then x1 depends on x2, x2 depends on x3 and x3 will in turn depend on x1, therefore what will happen, this thing will get completely messed up, right. So you can't write out a factorization like that, right. So one way of thinking about it is this thing is going to give you a set of conditional probability distributions, right. So each node is going to have a set of conditional probability distributions. So x1 is going to have a distribution which gives you x1 given x2 x3, likewise x2 will have a distribution associated with it which will give you probability of x2 given x4. So if I take the product of all these conditional probability distribution, I will recover the joint distribution of those variables. Okay, so that is basically the semantics associated with it, right. If you take the product of all this conditional probability distribution, I should recover the joint distribution of all the variables. So if you are going to have cycles, then that property will no longer be satisfied. So we do not want cycles in this case, right. And what else? Yeah. So it is a DAG where each node is a random variable, okay, and each edge represents a conditional dependence, okay, great. So because of the nature of the graph we are drawing, right. So the graph encodes a lot of separation rules. So what we mean by separation rule? It tells me that x1 is independent of x4 given x2, right. So I would say that x4 and x1 are separated by x2, right. So likewise, can you say something about x6 and x1 separated by x3? What about x7 and x1?
By x3.
x3, right. What about x6? Would x6 separate x7 and x1? No, x6 will not separate x7. What about x6? Will it separate x7 and x3? No. Right, so you can see where we are going with this, right. So I have shown you one separation rule, right. If there is a directed path from x4 to x1, right, directed path from xj to xi, any node along the path will separate xj and xi, provided that is the only path. If there are multiple directed paths, okay, it has to appear on every one of those directed paths, then it will separate it, or you will have to have a set of nodes. These two nodes together will separate xj and xi. So you will have to select one representative from each of those directed paths, then it will separate it. Because we will have to consider directed edges here, this is not called separation, it is called directed separation or deseparation. Come on, obvious terms, right, just make them up. Okay, so deseparation. So there are 3 deseparation rules, very simple deseparation rules, okay. J deseparates I and k, that is the rule we already saw, okay. So what do you think about this? If I know j, I and k are independent. See, that is basically what we are. If I know j, I and k are independent, right, they are separated. If I do not know j, they are connected. So knowing j, okay, separates them. Likewise, knowing j, will it separate I and k here? Yes. So again think about this, right? Suppose I didn't know j, right, but I know I, let us say something like this, right. So I know that x1 has a value of 1, right, I know x1 has a value of 1, right, and I know that x1 will be 1, right, only when, or rather I will know that I is 1 with a high probability if j is 0, right. So if I know that I is 1, then I know that the probability of j being 0 is higher. So as soon as I know the probability of j being 0 is higher, then I will know something about k, right, because there is a direct influence from j to k. But if I knew j, I know that j is 0, I do not care what I is, I can be anything, but knowing I will not tell me anything more about k than I get by knowing j, right. So in this case knowing j separates I and k, in this case knowing j separates I and k. Is there anything else that we need to worry about? Any other combination? Sorry? So these are I, j, k all the way, yeah. Anything else that is substantially different? Convergent, right? So what do you think?
Knowing J separates I.
Knowing j
Separates I and K.
Doesn't tell us.
Knowing J does not do anything. No, sir. Knowing J does not do anything.
huh? Doesn't affect, it is actually something else it does. Not knowing j separates I and k, knowing j connects I and k. Think about it, knowing j connects I and k, because let us go back here, right. So I know that xi is 0, I know that xi is 0, I know that x2 is 1, no, I know that x2 is also 0, right, I know that xi is 0 and I know that x2 is 0, then what about x3? Right, both are 0, then the probability of x3 being 1 goes slightly higher, right, because this is the case where both zeros occur with a higher probability, right. So we have this situation here. So if I know x2 is 0, I do not know anything about x1, I can't say anything about x3, does not matter, right, x1 and x3 are independent, I mean x2 and x3 are independent if I do not know x1, right. If I know x1, then x2 and x3 become connected. Does that make sense? Yes, right. So that is, these are the 3 d-separation rules. In both these cases knowing it separates, right, in this case not knowing j separates, in fact it is slightly stronger also. I can look at any descendant of j1, right, knowing any of the descendants of j1 also will end up connecting I and k. Not only should I not know j, I should not know the value of any of the descendants of j also, because as soon as I know the value of j1 I can make an inference about the value of j, and now that will help connect I and k, right. Not only should I not know j, but none of the descendants as well, okay. So these are the 3 d-separation rules. So it is great to see the d-separation rules did not actually talk about the values of the probabilities, right, it is just a representational thing. So I can plug in whatever values I want, all I am saying is just from the structure of the network I can tell you something about the separation properties, right. So the actual probability values could come in later, right. The values I used there were only for illustration purposes, did not necessarily be that, right, just the structure of the network itself tells you that what are the separation properties. Okay. Good. Any questions on this? This is clear. I can give you a very large graph, right, and ask you, okay, are A and B separated if I know C, D and E? Okay, what should you do then? Sorry? You have to find out all the paths directed and undirected between A and B, because I mean these are all undirected things, right. This is only one that goes along the directed path, right. This is actually an undirected thing, right. So I will have to look for all such paths between A and B and figure out, now do C, D and E. I given you C, D and E as the variables that are known, right. Figure out whether knowing those variables disconnects the path, and all the other variables are unknown, right. So you have to apply the third rule for the unknown variables as well, right. Then if all the paths get disconnected between A and B, then you say that A and B are de-separated by C, D and E. So this is a kind of analysis that you can do to make sure that you understand your system properly, right. So one of the original motivations for proposing this kinds of belief networks, this kind of DAG representation for the variables, was to study causality, okay, was to figure out causal relationships and so on and so forth. So these kinds of networks are also sometimes called as causal networks, and typically when you talk about causal networks, you do not associate the conditional probabilities with the thing. So just you are talking about A causes B kind of relations, right. You are not really worried about the probabilities in that kind of a setting, and so the same representation can be used for representing causality also, right. A causes B, right. So that kind of relationships can be represented using the same representation, but in general when you are using this as a Bayesian network, you do not imply any causality. This is something which you have to keep in mind when you are using it in practice, right. So you are not implying any kind of causality, right, when you are using this direction. This does not mean that I actually believe that x2 causes x1, right. When you are using it as a causal network model, yes, okay, when you are putting in an arrow here, that means you have thought about it and you believe from the physics of the system or whatever it is that x2 actually causes x1, right. And it turns out that when you are trying to do this, learn this graphical structure by just observing the system, looking at the data and trying to infer this kind of graphical structure between the variables, the most compact structure that you can derive will turn out to be the one that corresponds to the actual causal nature of the system, right. If you do it in a incorrect fashion, right, you will end up adding a lot more spurious dependencies between variables, right. If you are doing it in the correct causal ordering, then you will end up having a much more compact graph than you would if you are doing it at willy nilly, right. So what is the use of doing all of these things, right. I talked about this major modeling business. What is the use of doing all of this? So essentially we are interested in answering queries about variables, right. So no class, no lecture on graphical models or Bayesian networks is complete without you looking at the earthquake network at least once, okay. It is a very popular network for historical reasons, right. So you have a burglar alarm in your house, okay, and the alarm rings, okay. The alarm could ring because of two things, right. It could ring because there is actually a burglary. It could also ring because as okay. So this network was originally made up by Judea Pearl, okay. He is one of the early pioneers in the study of causal networks and belief networks and so on and so forth. So Judea Pearl lived in LA, lived in California. He was not thinking of wild animals, You are thinking of something else. Remember what I call this network? Okay. So probably the most two common occurrences in California, earthquakes and burglaries. Huh? Fire alarm, no, it's a burglar alarm. I am not interested in a fire alarm, I am interested in burglar alarms. Okay. And it turns out that Pearl had two very nice neighbors, right. Okay. Who would call him at his office and tell him, hey, your burglar alarm rang, okay, with some probability. Right. So this is basically, so if the alarm rings, Mary or John will call Pearl in his office and tell him that, hey, your alarm rang. So you can think about the causal directions here, right. So the alarm will be caused by the earthquake or burglary, right, and then Mary will call and John will call if the alarm rings. Okay. Both of them might call or none of them might call because they are all probabilistic things, right. So now I can ask questions like this. Mary called me and said that there is a, she thought she heard the alarm, okay. So what is the probability that the alarm rang? Both Mary and John called me and said both of them thought they heard an alarm. What is the probability that the alarm rang? I know there was an earthquake in my place, but both Mary and John did not call me. What is the probability that the alarm rang? Huh? What's that? Dead, is it? Good point. No, but if that is going to happen, see that is going to happen, I should have had an arrow like this. Okay, since I don't have the arrow, I am going to assume that this is not a likely event. Okay. That's what I am saying, right. If the earthquake is actually going to directly influence John and Mary's behavior, whether they are the question of their mortality or not or other things, right. So I would need to put an arrow directly between earthquake and Mary. Just assume that Pearl and Mary live in different earthquake zones, right. There is this one small fault line which will only shake Judea Pearl's house and go away. Come on guys, this is just an illustrative example, don't take it too much to heart. So the point here is I can ask all kinds of queries on variables on this, right. I can ask you even other things like that. Hey, Mary called, what is the probability that a burglary actually happened? Right. Mary and John called, what is the probability that a burglary actually happened? Does things change or not? Change or not?
Change.
No, you know everything to answer that question, yeah. Huh? It will change. It will change because if both Mary and John call, then my belief that the alarm rang goes up, right. If my belief the alarm rang goes up, then whatever belief I had about burglary happening will also automatically go up. Right. Now we know why these are called belief networks, right. So when I say Mary called, then my belief on whether the alarm actually rang or not changes, right. Base I have some belief on the alarm ringing, so I think okay, if nobody calls the alarm has not rung, okay, if Mary calls then basically I will flip this backwards, right. Here this will actually be only probability of Mary given alarm, right. So this is the probability I have here, but now given that Mary was 1, what is the probability of A being 1? But given that Mary and John are 1, what is the probability of A being 1? And given the probability of A being 1, what is the probability of burglary happening, right. So all of these things I can do all kinds of reasoning about the system based on just this whole model that I am learning, right. So I can ask all kinds of questions. I can ask questions about joint distributions, right. So Mary called, okay, what is the probability that the alarm rang and that John will call? Yeah, kind of a redundant probability, but still you can try to ask questions like this, right. Or I know that the alarm rang, somehow I know that the alarm rang, what is the probability that Mary and John will call me? So I can ask all kinds of questions. I can ask conditional questions, I can ask joint probability questions, and I can ask conditional probability questions, right. And if you think of this as classification problem, I can ask questions about, okay, I know these 5 variables, what is the probability that this is class 1? See, we got around our naive Bayes problem, right. So I said, what if you observe some variable whose values you have never seen before, how will you estimate the probability? I can still do that, I can just assume that the variable is unobserved and I can estimate the probabilities, right. It will actually give me valid answers, that given that I know A, B, C, what is the probability that class is 1. I might have another D, E, F, G, H, I, J, K which I have not observed, that is okay. So I can ask all these kinds of questions, right. Given partial data, now I can ask questions about classification, right, or given class labels I can ask questions about class condition densities, right. So given that it is document on cricket, right, how often will I do not know, let me not pick on any cricketers, poor guys. Given that it is a document about football, how often will the word Ronaldo and goal occur together in my document, right. Yeah, if you leave it to my son, he will say the probability should be 0, but but I know this is almost religious, right, the camps. Yeah, anyway, right. So that is the whole idea, right. So these kinds of questions, these kinds of queries that I ask about these variables, so we call this problem as the problem of inference on a graphical model, right. The problem of inference on a graphical model essentially is to figure out all these conditional probabilities or the marginal probabilities that we are interested in, right. So we looked at naive Bayes, right. So can you think of drawing the naive Bayes assumption as a graphical model? Every node is independent. Every node is independent, is it? So that will be like this. Is that my graphical model? No. What is the naive Bayes assumption? Given the class they are independent. So where should the class be? The top or at the bottom? And of course I can draw it wherever. The question is the direction of the arrows. Okay, let me draw it at the top. So people tell me how the arrow should go. Down, right? You will be surprised how many times people actually draw the arrow up. The reasoning is the variable values are the one that causes the class to happen, right. So if x1 is this, x2 is this, x3 is that, then they should all be influencing the class variable, therefore the arrow should go up, okay. Well, that is a fairly valid argument, it is just that it does not capture the naive Bayes assumption. That is a different kind of assumption that you are modeling there, right. So each variable is somehow affecting the class, it is essentially the opposite of naive Bayes, okay. It is essentially a complete model, right. So it is essentially all the variables are influencing the class, right. If in fact if you think about it, right, given the class, what happens in that case? All the variables get connected. It will be this case, right. So if all the arrows were going up, it will be this case. So if j was known, then all the variables get connected, right. In this case it is opposite of naive Bayes, right. Given the class, all the variables are dependent on one another, that is the assumption. If you draw the arrows upwards, right, the arrow should go down. Well, up and down is relative, right. The arrow should go away from the class node.